Marching band of fish, round and round they play their tunes, to golden songs of silence. Good morning, good afternoon, good evening. Thank you for tuning in. I'm your host, Somitsu. In this tutorial series, I'll be showing you how to make this flock of goldfish from scratch, with just the use of geometry and shader nodes. In order to make realistic looking flock without spending enormous time, there are 3 points of emphasis that I'll explain in the videos. 1. Look ahead alignment. 2. Multi-object instancing. 3. Movement animation syncing. I'm planning for this series to be a total of about 2 hours long, broken down into 6 episodes. It might be a long journey, but I promise you stunning results at the end. Alright, let's get into it. We'll start off by making a flock controller for the school of fish. For that, I won't be using buoys, which are typically used for flock control. Though I'm a huge fan of that algorithm. Due to its unpredictable nature, I came to a conclusion that it is better to just create my own with geometry nodes. So, the flock controller I'll be showing you is a curve-based controller with simple parameter tuning. Alright, as soon as we get into Blender, we'll hop into geometry nodes layout. A to select all, X to delete. Shift A, add a curve Bezier. Then, on data panel, crank up the curve resolution to 64. We won't be needing the spreadsheet for this, so let's expand the 3D viewport. Next, click on New to create a geometry node map. Then, type N to open up the side panel to rename input to curve, just to specify what type is expected. Then, add a join geometry and move the group input below it. At the end, we aren't going to be outputting this curve, but we'll use it as a reference while making the node tree. So, to make a flock, we'll start off with points to calculate position and movement, then later instance fish mesh on top. So let's add points node and connect it to join geometry. Point seems too big, so let's reduce its radius to 0.05 meters. Next, we'll place the point on the curve. First, duplicate the group input with Shift D, then connect the curve output to geometry input for sample curve. Change the sampling type to length, then enable all curves. Add a set position node after points, and connect the position. Point is now placed on the curve, and its placement can be controlled by adjusting this length. Next, let's make it so we can control the number of points externally by adding a group input to count socket of points. Open up the modifier tab, then input 3 into count. We want initial position to be random, so pull out a random value from length socket of sample curve. Then, connect index to ID and group input to seed. We'll leave the argument name as seed. Currently, the range of placement is within 1 meters of curve length. So duplicate a group input and connect the curve length. Then connect the result to random value max. Now, initial placement is within the entire length, but it seems a little congested at the end. So I'm going to set the seed to 1 instead. Alright, let's start adding some movement. After the random value node, pull out a mass add. Points will move uniformly according to bottom value, so connect the scene times second to bottom socket. Running the animation will cause points to move from left to right. All points are now jammed up at the end, so let's make them loop instead. Insert a floor module after the add. Then, connect the curve length output to the bottom socket. This will cause points to loop indefinitely. Next, let's control the speed by adding a multiply after the scene time. We want to make the base speed controllable from outside, so connect a group input from the bottom socket. Rename the argument to base speed. We'll just leave the value at 0.5 for now. Next, let's have points move at different rate. Insert a mass multiply after group input. Then, connect the random value to the bottom socket. Connect index to ID and group input seed to seed. Then, pull out a subtract from min socket and set the top value to 1. Pull out a group input from bottom socket to make it into an argument. Call this speed randomness. Set the default value to 0, min to 0, and max to 1. When randomness is set to 0, all points will move at base speed. Setting it to 1 will cause speed to be between 0 and base speed. So now the individual speed is set, let's reorganize a bit. There seems to be a very slow point, so I'll reduce the randomness to 0.5. We now have a general direction and speed of the flock. However, as you can see, all the points are just following a single line. We want individual points to have their own path. So what we'll do is add a noise to make the points veer off course. Instead of controlling with one noise though, we'll separate out the horizontal noise and vertical noise. The reason for this is each animal have different vertical and horizontal movement characteristics. Fish wiggles its spine side to side for thrust, so they have quicker horizontal movement. Whereas birds are more nimble vertically since their wings flap up and down. So we should make the noise tunable depending on what type of flock we're controlling. We'll first start off with horizontal noise. Add a space after the set position and insert another set position node. Add a noise texture and set the dimension to 4D. Then, set the detail, roughness, linearity to 0. Plug in a group input into scale and make it into an argument. Pull out a subtract from factor and center it to 0 by subtracting 0.5. Then, add a multiply to control its strength. Connect a group input to the bottom socket. For the arguments, rename scale to H noise scale and value to H noise gain. Next, connect the result to Z socket of combine XYZ. Pull out a cross product from tangent output of sample a curve. Then, connect it to the result of combine. Lastly, connect the result of cross product to set position offset. The horizontal noise is complete. If you run the animation, you'll see the points swing side to side. And you can confirm there's no vertical offset by changing to side view. Let's set the scale to 1 and gain to 2. As you can see, all points are tracing a single path. We want all points to reference different position and noise texture, so connect a random value to the W socket. Set the max value to 1000, connect the index to ID and group input seed to seed. Now, all points should be tracing different paths. Alright, Let's now add vertical noise. Create some space after set position. Then, select these nodes and Shift D to duplicate to the right. Add a set position node and connect the result of combine XYZ to offset. The arguments are that of horizontal noise, so let's delete these two group inputs. Then, connect them up to new group inputs. Rename the argument to V noise scale and V noise gain. Now the vertical and horizontal parameters are separated out. We'll just set the vertical values to 0.5 and 1. Alright, now select these nodes and Ctrl J to frame them. F2 to name it to horizontal noise. Frame the right side as well and call it vertical noise. The point movement is complete for now, so let's reorganize. We don't need the original curve anymore, so let's delete these nodes. Then, we'll rename the node group to flow control. Okay, there's more to do, but let's glance over what we made so far. Please check the connections and value settings. Now we'll delete this node group by clicking on this X. Curve will reappear, so click on New again to create a new map. Then, add the flow control we just made and drop it on the connection. I'm just avoiding using Ctrl G since it causes group input to automatically reconnect. Let's re-add the join geometry and group input to show the reference curve. Re-input the argument values. Count 3, seed 1, base speed 0.5, speed randomness 0.5, H noise scale 1, H noise gain 2, V noise scale 0.5, V noise gain 1. Should be the correct setting. The point movement seems decent, but in order for it to look organic, we'll need a lot more work. Let's cameo Suzanne to show you what I mean. With object mode, Shift A and add mesh monkey. S, then 0.1 to scale it down, then R, Z, 90 to rotate on Z axis. Reselect the Bezier curve and add instance on points after flow control. Then, drag and drop Suzanne and change setting from original to relative. Connect the geometry output into instance input. Let's hide the original Suzanne so only the moving ones are showing. So if we run the animation, we'll end up with this. Does this swing head moving look organic? With their faces facing in the same direction all the time, their movement are very unnatural. So in order to look organic, we must put a lot of consideration into its facing direction. This is my bullet point number 1. Look ahead alignment. In the past, it has always bothered me when using algorithms like Boyd's. we tend to align object to its movement tangent. It is not physically correct, so let me explain. Fish can only thrust towards where its body is pointing. If we place fish on this circle with tangent alignment, there's no way fish can turn this curve. Momentum and thrust vector is facing the same direction, and nothing is pointing towards the center. This is equivalent to turning a vehicle with a straight steering wheel. It's just not possible. Due to the state-based nature of buoys, tangent alignment is pretty much inevitable. However, if we can pre-calculate future position, we can use look-ahead alignment. This is a method that we align the body towards a future target position. In this scenario, turning force is generated by a mismatch between thrust and momentum, thus creating a circular path. It is equivalent to vehicle drifting in circular motion with its tail sliding outwards. Okay, so let's align it this way. Let's add some nodes in flow control to pre-calculate its future position. After the scene time, insert a mass add, then connect it up to group input. Call the argument look-ahead time. Set the default value to 0. Tap to exit from the node group and set the value to 0. Now, let's connect up the flow control arguments to empty socket of group input to control them externally. Next, duplicate the group input and flow control and bring them down. Disconnect the look-ahead time on the top and confirm the value is set to 0. Then, set the bottom look-ahead time to 0.2 via external input. When we connect up the viewer to flow control, we can see that the bottom points are placed a little ahead of top points. It is because top is calculating the current position, whereas bottom is calculating position 200 milliseconds in the future. Now this pre-calculation method is only possible since flow control is non-state based and deterministic. State-based buoys cannot utilize this method. Now, let's pull out a sample index from the bottom flow control. Change the type to vector. Connect value to position and index to index. Next, duplicate the position node, then subtract it from the sample position using vector mass. We're essentially subtracting the current position from the future position. Then, use normalize to turn it into a unit vector. At this point, we know the vector we need to align the fish towards. So let's now consider how fish mesh should align to the vector. I'm going to bring in my Tosakin for this guest appearance. So fish basically only have 2 rotational freedom. Z rotation for yaw, deciding horizontal direction. X rotation for pitch, deciding vertical direction. If your fish is doing Y rotation, it is about to die, so take him to a vet. We want to make sure to set the Y rotation, so negative Z is always pointing downwards. I'm going to reset the rotation of Suzanne head to negative Y direction with Alt R, since I want negative Y to be the standard forward direction for object instance. Next, since align rotation vector node does not have a negative Y option, I'm going to scale the unit vector by -1. Then, connect up the result to vector input of align rotation to vector node. Set the axes to Y and pivot to Z. Then, Ctrl-Shift-D to duplicate with connections and move it to the right. With result of scale connected to vector input, change the pivot to auto and connect the rotation output of the left to rotation input of the right. Lastly, connect up the result to rotation input for instance on points. When you run the animation, you can confirm that the bottom of the head is always pointing towards -Z, and it will pitch based on the X rotation. Even if we were to edit the curve, it has correct fishy turning behavior. Okay, we're almost done, so let's clean it up a bit. We want to make the instancing object into an input, so delete the object info and connect a group input instead. Reorder the arguments, and I'm going to also rename geometry to reference curve. Lastly, I'm renaming the node group to Flock Controller. And deleting it with X button. Click on New and reinsert the Flock Controller. I'm going to resummon Suzanne as a placeholder until fish mesh is complete. They should behave the same if you input 0.2 seconds to look ahead time. So, I know there's an issue with directional vector flipping at the end of the curve. I'm not going to fix that, since start and end point of the curve should be hidden from the final shot anyway, due to fish mysteriously appearing and disappearing at those points. And also for this tutorial, I'm planning to use circular paths, so it should be a non-issue. Alright, let's go over what we made. Here's the content of Flock Controller. Next, flow control. We're using basic speed calculation and noise to derive a position. Okay, I'm not planning to show how during this series, but this flock controller can be tweaked to control a bunch of ants or make huge sardine tornadoes. Try it out for yourself if you're interested. For the next episode, I'll be making a goldfish mesh and animation from scratch with just geometry nodes. Hope to see you then.